In today's lecture, we proceed to our next chapter. Chapter number 4 discusses about number theory. So in the previous lecture, we learned a little bit about modular arithmetic. So in this chapter, we will go deeper. Okay, so we discuss more about the modular arithmetic. So what is set of residues? So basically, the set of residues is denoted by Zn. Z sub n, Z means the entries for this set only for integers. Only integers allowed to be members for this set. And why there is a subscript n? Okay, so n here is a natural number. So we consider n as a natural number. Okay, so the set of residue, which is denoted by Zn, is the result of modular operation. Okay, we back to the modular operation. So modular operation is looking for the remainder. Okay, when we do the division, we are looking for the remainder. The result of modular operation, or simply known as mod, with modulus n is r, where the value for the r, which is the remainder, okay, is greater than or equal to 0. That means it could be 0, but then if it is not equal to 0, so it must less than n, which is the value of the modulus. Alright? So the modular operation creates a set. Okay, so the modular operation creates a set. So if we collect all the value for the r, so we put inside one set, so that set is what we call as the set of least residue modulo n. Okay, set of least residues modulo n, denoted like this. Okay, so the entries for this set start from 0, okay, 0 up to n minus 1. So exactly following this range. It could be equal to 0, so it moves from 0 up to n minus 1. So if n equal to 5, so the entries for the Z5 equal to 0, 1, 2, 3, and 4. Okay, so we have infinite instances of the set of residues. Why? Because the number n, which is the natural number, could be infinitely many. There are infinitely many candidates for the n, so there are infinitely many set of residue Zn. So one for each value of n. Alright, so I give you a few examples here. So the value for the Z7, okay, it starts from 0 up to 7 minus 1, which is 6. Z5 equal to 0 up to 4. And Z8 contains 0 up to 7. Okay, now about congruences. Okay, so we're back to the definition of congruences. Let's say we are given three integers a, b, and n, where the value for the n must greater than or equal to 1. If n divides a minus b, that means a minus b divisible by n minus b, when we divide a minus b by n, so the outcome is an integer q without any remainder. So that means a and b are congruent modulo n. A and B are congruent modulo n. So we use this kind of notation. We have triple horizontal lines, okay, to denote the congruent relation. And we need to put the modulus value inside the parenthesis. Okay, so make sure you write the notation correctly. You put the modulo inside the parenthesis. So we create this relation as A congruent B mod n. Okay, we have a few examples here. Consider the following congruences relationships. So remember, there are two modulo operations. There are two modulo relations which are quite different, but then quite related to each other. So first of all, we have a modulo reduction. Okay, we have, for example, this 12 mod 10 equal to 2. That means we are looking for the remainder when we divide 12 by 10. Okay, so we divide 12 by 10, the remainder equal to 2. We divide 2 by 10, so the remainder for integer equal to 2. Also, we divide 22 by 10, the remainder also equal to 2. Okay, that is what we call as modulo reduction. But for this modulo notation, so we are discussing about the congruence relation. Okay, congruence relation. When we are talking about congruence relation, we need to refer back to the definition. Okay, they look similar, but actually we're looking for the different thing. Okay, for integer 2, 12, and 22, okay, 2, 12, and 22. So actually these three numbers are congruent modulo 10, because when we reduce these three numbers, so by using the same modulus 10, so the outcome are the same. Okay, so the outcome are the same, equal to 2. So these three numbers, 2, 12, and 22, are congruent modulo 10. Alright. Okay, now residue classes. A residue class which denoted by this square parenthesis. Okay, we put R inside the square parenthesis and then we have subscript N. Okay, so this is what we call as a residue class. Okay, residue class. So a residue class is the set. So it is a set. So we need to enclose the entries inside this kind of parenthesis, curly parenthesis. The set of what? Set of all integers. Set of all integers A such that A congruent R modulo N. Okay, so any integer A that satisfies this congruent relation belongs to this set. Alright, so any integer A, doesn't matter it is negative, 0 or positive. So any A that satisfies this congruent relation, it is congruent R mod N, so it belongs to this residue class of R modulo N. Alright, so that means we are looking for the A when we minus with R and divide by N, so the outcome is an integer without any remainder. Okay, where R is restricted between 0 and N. So any number belongs to this set, or any number satisfy this condition belongs to this set. Okay, so we have few examples here. So if we let N equal to 5, that means the modulus value is 5. Okay, so that means we are looking for the A congruent R mod 5. And R, I give you 5 different numbers for the R. First of all, we are looking for the integer A, which give us R equal to 1 when we do the modulo 5, when we take 5 as the modulus. So any value A satisfied, this congruent relation belongs to this set. So we check one by one. Okay, so for this set, 16. So 16 congruent 1 mod 5. Is it true or not? 16 minus 1 divide by 5. Yes, it is equal to 3. 3 is an integer. So yes, 16 belongs to this residue class of 1 modulo 5. What else? We try 17. Okay, 17 minus 2. We divide by 5. Yes, again the answer is an integer. Okay, so this is the what we call a set of the residue class. Okay, so any element satisfy the condition as shown in the previous slide, so belong to the following set. So there are infinitely many. As you can see here, we have triple dot at the in front and at the back, so that means there are infinitely many elements for this sets. Okay, it can move to negative infinity up to positive infinity. Okay, now so the set of the residue modulo n, the Zn, okay, is a set. So means we can do operations inside the set. Okay, so the operations addition, subtraction, and multiplication are defined for the set of Zn. That means we can do all these three operations, and the outcome also belongs to the same set. Okay, that is what we call as define. Alright, so we do the operation. We have a 1 and 3 belongs to the Zn, and we do add the plus, minus, or multiply. So we let this operation as star, where star can be any one of these three operations. Okay, and then we have another number b, where a and b belongs to the Zn. So the outcome is another number c, and c also belongs to Zn. Okay, so that's why we say that plus, minus, and multiplications defined for the set of Zn. So how about division? Okay, for division, it is not necessary true. Yes, sometimes it is true, but sometimes, most of the time, it is not true. That is why the division operation doesn't define for the set of Zn. Okay, so we have the following operations: a plus b mod n, the outcome also belongs to zn, and so on. Okay. Okay, so although even if a and b doesn't belongs to zn, okay, we also can still do the operations, and we can do the modulo reduction to ensure the outcome belongs to the set of zn. Okay, after we do the modulo reduction operation, then the outcome of the following three operations will belong to the set of Zn. So I'll give you a few examples here. 7 plus 14, so the outcome is equal to 21. Okay, obviously 21 outside the set of Z for 15. So if we do the modular reduction mod n, which is 15, so the outcome is 6, and 6 belongs to the Z 15. So we can do the same operation for subtraction and multiplication as well. So we can obtain the outcome belongs to the set of Zn. Okay, so the following operations also are true. Okay, so let's say we have two integers a and b, especially when a and b are large integers. So it is good for us. It is advantageous if we do the modulo reduction step by step. That means instead of do the addition, subtraction, or multiplication directly, okay, maybe outside the capacity or capability of our calculator to do the calculation, so we can do the modulo reduction one by one. Okay, that means instead of directly do the multiplication, so we can reduce a mod n first. So to make sure the value for the a mod n belongs to Zn. Okay, that means small number. And b mod n also belongs to the Zn, that means smaller number than b. Then we do the multiplication. So if the outcome outside the set of Zn, so we can do again the modulo reduction mod n to make sure the outcome belongs to the set of Zn. Okay, so this idea totally advantageous when we deal with large numbers. Okay, give you a few examples here. Instead of do the addition directly, so we can do the modulo reduction first towards both numbers inside this parenthesis. So we do the modulo reduction here, do the modulo reduction here, do the outcomes of smaller numbers. Okay, you do the addition. Again, the outcome doesn't belongs to the Z11 set, so you need to do the modulo reduction again and make sure your final answer belongs to the set of Z, and in this case Z11. Okay. Alright, so the same case when we do the subtraction. So when the value is negative, it's very easy. Just need to add the value with the modulus until we obtain the first positive number, which is 10. So 10 belongs to the Z11. That is the final answer for the second example. And for the final third example also, we do the same steps. We do the modulo reduction inside the parentheses one by one. And finally, we reduce the final answer modulo 11, just to make sure the answer belongs to the set of Z11. Other than the set of residues Zn, we have two more sets, Zp and Zp star. Okay, so what is the difference between Zn, Zp, and Zp star? For the Zn, so n, as I mentioned before, can be any natural number. Okay, any natural number can be the integer n. But for the Zp, we restrict the value for the p only for prime numbers. Okay, what is the definition for the prime number? So prime number is any natural numbers greater than or equal to 2 which can be divided without any remainder by only two numbers. Okay, 1 and itself. Alright, 1 and itself. So that is what we call as prime number. So when we replace the n with p, where p is a prime number, so we have a Zp. Okay, Zp. So the entries for the Zp, just like the Zn, we start from 0 up to p minus 1. The only difference is p this time is restricted only to be a prime number, where n can be any natural number. It can be prime or composite, doesn't matter. Okay, so I give you two examples here. This one is for the Z7, where 7 is a prime, and Z11, 11 also is a prime. So start from 0 up to P minus 1. So how about the ZP star? For the ZP star, okay, for the ZP star, so the elements start from 1. Okay, for the ZP star, just like the ZP, but then the smallest entry for the ZP star equal to 1. Okay, because of this simple difference between ZP and ZP star, so actually ZP and ZP star differs in many aspects, especially in terms of their category. Okay, so I give you a few examples here. First is the property for the ZP. For the ZP has an additive inverse. So later I'll explain detail about this one. So each member in ZP start from 1 until P minus 1 has an additive inverse. And each member in ZP also has a multiplicative inverse except 0. So 0 in ZP doesn't have any multiplicative inverse. Okay, but if we exclude the 0, then it becomes ZP star. For the ZP star, each member in ZP star has additive and multiplicative inverse. Okay, that means if we exclude the 0 from ZP, so it becomes ZP star. So in the ZP star, all or each member in ZP star has an additive and multiplicative inverse. Okay, so the entries just like the ZP, but the only difference is the smallest element inside the set start from 1 and not 0. Okay, so modular inverses. Okay, so talking about modular inverses, there are two kind of inverses. Okay, there are two types of inverses there are two types of modular inverses. The first one is what we call as additive inverse, just like we mentioned in the previous slide. Additive inverse and multiplicative inverse. Okay, for the additive inverse, what does it mean? So when additive, that means the operation involved is addition. Okay, so if we have two numbers belongs to the Zn set, okay, so AB we belongs to Zn are additive inverses to each other. What does it mean? That means A is an additive inverse of B and B is an additive inverse of A. Okay, if both numbers A and B satisfy this condition. Okay, if A and B satisfy this congruent relation, A plus B congruent 0 mod n. So what does it mean? If we back to the definition of congruent relation, these two numbers are congruent when A plus B minus 0 divisible by n. When we divide, the outcome is an integer q without any remainder. So that means A plus B divisible by n. Okay, A plus B divisible by n. So if you're given one number, let's say the given number is A. So how to find the pair? How to find the additive inverse of A? So to find the additive inverse of A, which is B, can be found by using this simple equation. So B equal to n minus A. Okay, if we're given one of the number, so let's say the number we can denote as A, so we need to find B. So B can be computed as B equal to n minus A. Simple. Okay. I give you example. Suppose the additive inverse of 4 in Z10. Okay, so that means we are given one number. So this one is our A, this one is our N. So our n equal to 10, our a equal to 4. So how to compute b? B equal to n minus a, so it is equal to 6. If you try to verify, yes, 4 plus 6 equal to 10. And 10 is congruent 0 mod 10 because 10 is divisible by 10. Okay? So in modular arithmetic, each integer has an additive inverse. Okay? Whether in Zn, Zp, or Zp star, so all elements inside this set, okay, has an additive inverse. Okay, for additive inverse, yes, all entries has an additive inverse. Okay, now, quite complicated is the multiplicative inverse, but later on we see details about that one lah. But First of all, we need to understand about the additive inverse. So let's consider the following example. The question asks you to find all additive inverse pair. Okay, all additive inverse pairs in Z10. Okay, in this question, the only available information to you is n. We know that our n equal to 10. Okay, so how to answer this question? First of all, you need to understand. You need to know, you need to take note about all the entries for the Z10. So we have 1, 0, 1, 2, 3, 4, 5, up to 9. Okay, and the question asks you to find pair. To find pair. Okay, so we start from 0. So 0 plus 0 equal to 0. 0 congruent 0 mod 10. So we found the pair for 0 is equal to 0. So how about 1? Okay, so for 1, so we can let A equal to 1, our N equal to 10. So our B equal to 10 minus 1 equal to 9. So we obtain the pair for 1 equal to 9 because 1 plus 9 equal to 10. 10 is divisible by 10 and it is congruent 0 mod 10. Okay. Next, we can let our A equal to 2. Our N equal to 10. So 10 minus 2 equal to 8. So 8 is the pair for 2. Okay, so we do the same steps until we obtain the pair for 5. Okay, so how about 6? Okay, if for 6, so A equal to 6, then N equal to 10. So 10 minus 6 equal to 4. So that means the pair for 6 equal to 4. But then if we check the earlier step, we already have the pair for 4 equal to 6. So in additive inverse, 4, 6 equal to 6, 4 because we want to find a pair. Okay, doesn't matter the position, doesn't matter the order, doesn't matter. Okay, so 4, 6 equal to 6, 4. That means we need to write this pair only once. Okay, therefore the additive inverse pairs in Z10 are 0, 0, 1, 9, 2, 8, 3, 7, 4, 6, and 5, 5. So these inverses are reciprocal, as I explained before. So 4, 6 equal to 6, 4. So no need to write twice. Just need to write it once. Satu kali saja. Okay, once. So we have 4, 4, 6. Okay, so that's how we answer this question. Okay, so finish with additive inverse, which I think is too easy and too simple for you. So now we move to more complicated one, which is multiplicative inverse. So in multiplicative inverse, so multiplicative, that means the operation is multiplication. Previously, additive inverse, that means the operation is addition. Now the operation is multiplication. So if you're given two numbers, A and B, which belongs to Zn, okay, so these two numbers are multiplicative inverses of each other. That means A is A is multiplicative inverse of B and B is the multiplicative inverse of A. If both numbers satisfy this condition. Okay, A times B congruent 1 mod n. Previously, A plus B congruent 0. But this time for multiplicative, A times B congruent 1 modulo n. Okay, so I give you example. Suppose I give you two numbers 3 and 7 which belong to Z10. So we multiply these two numbers. So the outcome equal to 21. 21 congruent 1 mod 10 because 21 minus 1 equal to 20. When we divide by 10, so the outcome equal to 2 and 2 is an integer. Okay, so that means 3 is the multiplicative inverse of 7 modulo 10 and 7 is the multiplicative inverse of 3 modulo 7 because they are multiplicative inverses of each other. An integer may or may not. Okay, so in additive inverse, all integers in Zn, Zp, and Zp star has additive inverse. But for multiplicative inverse, an integer may or may not have a multiplicative inverse. That means we have a condition. In order to have a multiplicative inverse, we need to satisfy a condition. So what is the condition? So the condition is related to the greatest common divisor. So we learned about the greatest common divisor in the previous lecture, and we also learned how to find it. Okay, so now we use that concept as the condition for the multiplicative inverse. If the GCD of A and N, which is the modulus value, equal to 1, okay, the greatest common divisor of A and N equal to 1, then the integer A has a multiplicative inverse modulo N. Okay, that means the integer B exists such that A times B congruent 1 modulo N. Okay, so that means A has a multiplicative inverse modulo N if and only if the greatest common divisor of A and N equal to 1. So when it is equal to 1, we can say that A and B are co-prime or relatively prime. Okay, co-prime or relatively prime. Okay, when GCD of A and N equal to 1. So with any number, two numbers, when the GCD equal to 1, so we say that two numbers as co-prime or relatively prime. So in this case, we have A and N. Because A and N, the GCD equal to 1, so we can say that A and N are co-prime or relatively prime. So on the contrary, if the GCD not equal to 1, okay, the GCD of A and N not equal to 1, let's say 2, 3, and so on. So what does it mean? That means the integer A doesn't have a multiplicative inverse modulo N. Okay, that means the integer B doesn't exist. Alright, so please understand and memorize this condition before you calculate the multiplicative inverse. Check the condition. If there is an inverse, then proceed with calculation. Otherwise, just simply give me a conclusion that there is no multiplicative inverse because the GCD not equal to 1. Okay. How to find the multiplicative inverse efficiently? So we have an algorithm to compute the multiplicative inverse value. Okay, that means I give you A, I give you N, find the integer B such that A times B congruent 1 mod N. Okay, how to find B? We can use the we can use an extended Euclidean algorithm. Okay, so now we learn detail about this algorithm. So if the GCD of two numbers, let's say x and m equal to 1, so there exists the multiplicative inverse of x modulo m. So the multiplicative inverse is denoted like this. So it is an integer. So when we divide this integer with x, so the outcome, the product is congruent 1 modulo n. So what does it mean? That means x based on the definition, x inverse minus 1 divisible by m. The outcome is an integer. The integer x inverse modulo m is called as the multiplicative inverse of x modulo m. So that's the way how to pronounce this notation in full. Okay, multiplicative inverse of x modulo m. Extended Euclidean algorithm can be used to compute the value for the multiplicative inverse of x modulo m. Okay, so suppose we have two positive integers a and b, where a is greater than b. Okay, so there are another two integers denoted as u and v such that a times u plus b times v equal to the GCD of a and b. Okay, so this equation is always true for any integer a and b. Okay, for any positive integers a and b, there exist another two integers u and v such that au plus bv equal to the GCD of a and b. So this equation always has a solution. Now, we consider when the GCD equal to 1. So the equation 1 becomes the equation number 2. So we have A times U plus B times V equal to 1 because the GCD of AB equal to 1. From the equation AU plus BV equal to 1, we consider the following two cases. In the first case, we take AU to the other side. So the remaining value at the left hand side is B times V. Okay, we take AU to the other side. So we have BV equal to 1 minus AU. So now we take B to the other side. Okay, we take B to the other side. So we have the following equation. Okay, so we rearrange this equation 1. We rearrange, it becomes equation, the second equation. So we have AU, we put AU in front. Previously it is located here, but we take the value for the AU as positive, so negative, so 1 becomes negative and BV also becomes negative. Okay, in other words, we multiply this equation by negative 1. Okay, so we have the second equation. So we have AU minus 1 equal to BV. So if we take B to the other side, to the left hand side, so we have the third equation. So from the third equation, so we can refer back to the definition of congruent relation. So what from this equation, what we can obtain is we have AU congruent 1 mod B based on this equation, and also back to the definition of congruent relation. That means A times U congruent 1 modulo B. So from this congruent relation, what does it mean? That means the multiplicative inverse of A modulo B is U. Okay, because A times U congruent 1 modulo B. Okay, so the multiplicative inverse of A modulo B equal to U. So this is the first case when we take AU to the other side, okay, to the same side as 1. So in the second case, okay, we take BV instead of AU, we take BV to the other side. Okay, so now we have this equation. Okay, so similarly, if we multiply this equation by negative 1, so we obtain the second one. We have BV minus 1 equal to A negative U. So if we take A to the left hand side, so we obtain the third equation. So back on the definition of a congruent relation, because BV minus 1 divisible by A, the outcome is negative U. Negative U is an integer. So what does it mean? That means BV congruent 1 modulo A. So BV congruent 1 mod A means that, okay, the multiplicative inverse of B modulo A is equal to V. Okay, the multiplicative inverse of B modulo A equal to V. Okay. So now we move to the steps. Okay, the steps how we can find the multiplicative inverse. Okay, to compute the multiplicative inverse of x modulo m, so we need to consider the value for the x and m. If the value for the x greater than m, that means the multiplicative inverse of x modulo m equal to u, such that, okay, such that x times u plus m times v equal to 1. Okay, now that means if x equal to m, so we need to find this u which satisfy this equation. Okay, xu plus mv equal to 1. If you can guess two values u and v which satisfy this equation, then you obtain the solution. For u is the multiplicative inverse of x modulo m. Okay, if the value for the x less than m, then the multiplicative inverse of x modulo m equal to v, such that mu, we put m in front, we pair m with u, okay, plus xv, because x is smaller than m, then we pair x with b, v equal to 1. Okay, so v is the multiplicative inverse of x modulo m. So from these two conditions, that means if we are given two numbers x and m, so which number is larger, we pair with u. Okay, we pair with u. So any number between u and v which pairs with x is the multiplicative inverse of x modulo m. Okay, in this case, x is greater than m, so we pair x with u. So because x is paired with u, so the multiplicative inverse of x is u. The second case, x is smaller than m. That means m is greater than or larger than x. So we pair m with u. Okay, and x with v. Because x is paired with v, that means the multiplicative inverse of x modulo m is v. Alright, so if you can guess these two numbers, yes, you can proceed without doing the extended Euclidean algorithm, because just the same steps. Because in the extended Euclidean algorithm, we are looking for the same value u and v actually. Okay, so if you can guess, proceed. If you cannot guess, then we need to do the extended Euclidean algorithm. Okay, the following example is to show you how to use the extended Euclidean algorithm to compute the multiplicative inverse. So we consider this example. Compute the multiplicative inverse of 73 modulo 25. So we know that x equal to 73 and m equal to 25. Then we compare these two numbers. Okay, obviously x is greater than m. So what does it mean? That means we pair x with u. So x with u and v with m. So we need to find u and v which satisfy the following equation. Okay, because x is paired with u, so the multiplicative inverse of x modulo m equal to u. Alright. So now we proceed with the extended Euclidean algorithm because we cannot guess the value for the u and v which satisfy this equation. That means we need to proceed with the extended Euclidean algorithm. Okay. By applying Euclidean algorithm, okay, before I forget, this question doesn't specify the way how to solve this problem. Okay, that means if you can guess, then you can guess. But if not, you have to do the extended Euclidean algorithm. But if the question specifies the way how to solve the problem, for example, compute the multiplicative inverse of 73 and 25 by using extended Euclidean algorithm. So you don't have any option. Okay, you don't have any option. You have to do the extended Euclidean algorithm instead of simply guessing the answer. Okay, so the first step in the earlier step in the extended Euclidean algorithm is to do the Euclidean algorithm. Okay, basically it is an Euclidean algorithm, but it is an extended form of the Euclidean algorithm. That is why we call it as extended Euclidean algorithm. But the core of the extended Euclidean algorithm is the Euclidean algorithm. So we need to understand the Euclidean algorithm that we learned in the previous lecture. Okay, so why we need the Euclidean algorithm? Because we need to find the GCD of x and m. Okay, compute the GCD of x and m. Okay, so we have 73 divided by 25. The quotient equal to 2. The remainder equal to 23. So take note about the quotient. Okay, not the remainder. When we want to find the GCD, in the previous lecture, I told you that take note about the remainder. Okay, but this time we are looking for the quotient because the extended Euclidean algorithm needs the quotient value as the input, part of the input. Okay, so we take note the first quotient equal to 2. Because the remainder not equal to 0, we need to proceed. We take 25 as the new dividend and 23 as the new divisor. 25 divided by 23, the quotient equal to 1, the remainder equal to 2. Because the remainder not equal to 0, we need to proceed to the next step. But before that, take note about the value for the quotient. The second quotient equal to 1. Next, we take 23 as the new dividend and 2 as the new divisor. 23 divided by 2, the quotient equal to 11 and the remainder equal to 1. Okay, so take note about the quotient. The quotient equal to 11. Because the remainder not equal to 0, that means we need to proceed. So we take 2 as the new dividend, 1 is the new divisor. This time the remainder equal to 0, then we stop. Okay, so clearly the GCD equal to 1. Okay, because the earlier remainder before 0 equal to 1. So GCD equal to 1. So because the GCD equal to 1, there exists the multiplicative inverse of 73 modulo 25. That means we can proceed to the extended steps. Okay, if the GCD not equal to 1, then give me the conclusion. There is no multiplicative inverse because the GCD not equal to 1. That's it. No need to proceed with the next calculation steps. Okay, because the GCD equal to 1, that means there exists, these two integers exist such that 73u plus 25v equal to 1. Our aim is to find this u. Okay, to find this u. Not v, but u. So in the next step, we compute the value for the u. Okay, so by default, for the u, we have the following two fixed values. We have u naught equal to 1, u1 equal to 0. You have to remember these two fixed values. u naught equal to 1, u1 equal to 0. Then we compute u2. Okay, so we compute u2 equal to negative q1 multiply with u1 plus u naught. The outcome is equal to 1. Okay, so finish with u2. We move to u3. u3 equal to negative q2 multiply with u2 plus u1. The outcome equal to negative 1. And the next one is u4 equal to negative q3 times u3 plus u2. The outcome equal to 12. Then we stop because previously we only considered 3 quotients. Okay, the final quotient, no need to consider the final quotient. You only consider the quotients before the remainder equal to 0 because we have q1, q2, q3. So we need to compute until u4 because u4 using the final quotient which is q3. There is no more quotient, then we stop until u4. So where is the answer? The answer is the final u which is u4. So this is the desired u, which is the multiplicative inverse of 73 modulo 25. Okay, let's say the question asks you to verify. So how to verify? Is it true that 12 is the multiplicative inverse of 73 modulo 25? Yes, we can verify. We back to the definition of multiplicative inverse. So we multiply these two numbers. Okay, we obtain 876. So 876, okay, is congruent 1 modulo 25 because 876 minus 1 is divisible by 25. Okay, the next example, compute the following two values. So this time, I think just like the previous one, because we have x greater than m, so we do the same steps. We do the Euclidean algorithm. We take note all the quotients before the quotients when remainder equal to 0. So no need to consider this one. Okay, so we stop until the quotient 6. Okay, so because the remainder before remainder 0 equal to 1, that means the GCD equal to 1. Because the GCD equal to 1, so there exists this u. The multiplicative inverse exists, so we can proceed to compute. Okay, so we compute the value for the u. This one, these two values are fixed. We continue until u7 because we have until q6. Previously, we consider until q6. That means we need to compute until u7. So the outcome is negative 252. Okay, when the value of u is a negative value, so you need to convert it to positive value. Okay, although this equation true, when we substitute yes, u and v, so the equation true, but then since the value is less than 0, you need to convert it to positive value. How? By simply add with the modulus value and take the first positive value. Okay, so the first positive value after we do the addition, negative 252 plus 583. The first positive integer appear is 331. So the multiplicative inverse of 738 modulo 583 is 331. Okay, so don't give the negative value as the final answer. Make sure you convert it to positive value. Okay, so this is the way how to verify. Yes, the obtained value 331 after we convert the value to positive value also true. Okay, because these two numbers divisible when with with 1, it is divisible by 583. Okay, in the next example, we have different case when we have x smaller than m. Okay, so when x, which is 6, is smaller than m, which is 35, so our aim is to find v such that 35, which is m, okay, u plus our x is 6v equal to GCD, this one. So our aim is not to find u, but to find v. Okay, but the next step, just like the previous example, so we do the Euclidean algorithm. So in this case, we only consider two quotients value, because at the third quotient the remainder equal to 0. So we stop here, because the remainder before it is equal to 0, it is 1. So that means the GCD for these two numbers, 6 and 35, equal to 1. That means the inverse exists. The inverse v exists, so we can proceed to the extended steps to compute v. Okay, because the inverse is v, so we compute v, but to compute v, we need to compute u first. Okay, so if the inverse is u, no need to compute v, but if the inverse is v, we need to compute u. Okay, because we obtain u, then we can obtain the v. Okay, so we use the following these fixed values, and then we compute u2, u3, because the q we have only until q2. So the value for the u3, which is the desired outcome, is equal to -1. We need to, okay, we insert -1 into the equation, 35u plus 6v. So we substitute this u equal to -1, and then we can solve this equation, because the remaining unknown value is v, so we can solve this equation for v. So v equal to 6, because 6 is already positive number, so no need to convert this number. So just maintain the answer equal to v. So the multiplicative inverse of 6 modulo 35 equal to 6. So this is the way how to verify if the question asks you to verify. Alright, next we move to the linear Diophantine equation. Linear Diophantine equation. So what is linear Diophantine equation? So it is an equation. Okay, it is an equation. That means it has this equal sign. It is an equation which has two variables. Okay, two variables. Okay, the LDE, the linear Diophantine equation of two variables. Okay, it can has more than two variables, but for two variables case, so we have the following type of equation. So we have ax plus by equal to c. Okay, where a, b, c, x, and y are all integers. So why two variables? Because the considered two variables are x and y. Okay, so this is the linear Diophantine equation of two variables. So if we have more than two variables, we have three variables. For example, so LDE of three variables, so we have a x plus by plus cz equal to d. So this is an LDE of three variables, but in our lecture we only consider this kind of case. Okay, alright, so what is the problem in the linear Diophantine equation? In the linear Diophantine equation, normally we are given only two values, three values. We are given three integers, a, b, and c, and our task is to find two unknown values, which are x and y, which can satisfy this condition. Satisfy means we need to find x and y which can make this equation true. Okay, so the solution for the linear Diophantine equations relies heavily on the value for the greatest common divisor of a and b. Okay, remember our equation is ax plus by equal to c. If the GCD of a and b, okay, a and b equal to d, if d divides c, if the GCD value divides c, means C is divisible by D. That means the LDE has infinitely many solutions. There are infinitely many solutions. Okay, when the GCD D divides C, C divides by D, the outcome is an integer, then that means there are infinitely many solutions for the different time equation. But if the D, which is the GCD of A and B, doesn't divide C, okay, when we divide C by D, the outcome is not integer. Okay, that means the LDE has no solution. No need to compute because there is no solution. Just give me the reason why there is no solution, because D doesn't divide C. So if they divide C, a particular solution. So when there are infinitely many solutions, that means we have two types of solutions. We have particular solution and also general solutions. If D divides C, a particular solution to the LDE, number one, can be found by using the following steps. The first step is to reduce the equation 1 to the following form. Okay, we divide the equation number 1, we divide by D. Okay, so we divide A by D, B by D, and also C by D, because all these numbers are divisible by D. Okay, so we divide, so we obtain this equation. Okay, we obtain this equation. Next, solve the following equations for S and T. Okay, so we have the smaller value of A, we denote as A1 after we divide by D. So that means A divided by D, the outcome is A1. So A1 plus B1. B1, okay, we divide by D, sorry. B, the original B, we divide by D, the outcome is B1. So A1 times S plus B1 times T equal to 1. So we need to find S and T which satisfy this equation. Okay, how? By using the extended Euclidean algorithm. Okay, by using extended Euclidean algorithm that we learned previously. Okay, because the extended Euclidean algorithm will give you the value for the S and T. Previously, we used U and V. Okay, S and T will satisfy the following equation. So once we obtain the value, okay, for the S and T, then we can find the particular solution. So the particular solution is denoted by X naught and Y naught. So the value for the X naught, it is equal to C over D multiply with the value of S, which is obtained by using the extended Euclidean algorithm. So how about Y naught? Y naught also is obtained by the same way. We multiply C over D, but this time with T. Okay. So the key point here is the extended Euclidean algorithm. If you understand about the extended Euclidean algorithm, then you don't have any problem to solve this problem to obtain S and T. Once you obtain S and T, then you can solve these equations to obtain the particular solutions X naught and Y naught. So finish with the particular solution. Now we move to the general solution. So general solution denoted simply by X and Y. So the general solution for the X equal to X naught plus B over D, we multiply with K. Okay, and for the Y, it is denoted by Y equal to Y naught, which is the particular solution for Y, minus. Okay, for the X, it is plus. For the Y, it is minus. Okay, that is why I highlighted these two operations, because they are crucial. Okay, so Y naught is minus A over D multiplied by K. So for K, K can be any integer. You can write like this. K can be any integer. So the general solution means if you substitute K with any integer, 0 or any integer, so the outcome is the solution for the linear different time equation. Okay, because these two equations are general solutions for the given LDE. So you can replace K with any integer, X and Y still satisfy the LDE. Okay, I'll give you example. Find the particular and general solutions to the following LDE. Okay, so note that our A equal to 21, B equal to 14, and C equal to 35. The first step is to find the GCD 21 and 14. Okay, this can be done by using the equivalent algorithm. So find the GCD. Why? Because we want to know whether the given equation has solution or not. Okay, so we need to find the GCD first. So in this case, the GCD equal to 7. Okay, because here this one is the remainder equal to 0, so the GCD is here. GCD equal to 7. So now we check whether 7 divides D as C or not. Okay, because our C equal to 35 kan. So 35 divide by 7, the outcome is an integer. So that means there are infinitely many solutions for this LDE. Because 7 divides 35, the given LDE has infinitely many solutions. So we start by finding the particular solution for the LDE. So the first step is to divide, okay, both sides of the equation by 7. Okay, we divide. Okay, what is our original equation? Our original equation is 2114. 21x plus 14y equal to 35. So we divide this equation by 7. So we obtain this one, equation number 2. Okay, so equation number 2. Okay, we have our A1, we have our B1, so we need to solve this equation. Okay, remember the GCD now, the value at the right hand side now is equal to 1. Okay, not 5. So we have 3s plus 2t equal to 1. Okay, as I mentioned before, if you can guess the value for the s and t which can satisfy the equation 3, then guess. No need to use the extended Euclidean algorithm. Okay, because the question doesn't ask you to do so. Okay, so just guess. So we need the extended Euclidean algorithm when you cannot guess the value for the s and t. Okay, so in this case, yes, we can guess. We can take s equal to 1, t equal to -1, then we can satisfy this equation. We can make this equation true. Okay, so that means we already have our s and also our t. Then we are ready to compute the particular solutions. So the particular solutions, okay, we are looking for the x0 and y0. For the x0, it is equal to 5. And for the y0, it is equal to -5. So let's check whether these two values are solutions or not for the given LDE. After we substitute x0 and y0, yes, it they satisfy the given LDE. Okay, so finish with the particular, we move to the general solutions. For the general solution, we're looking for the x and y. So we substitute all the values and then we just remain this one as k. Okay, so we have x equal to 5 plus 2k and y equal to -5, -3k. And don't forget to mention about this one. K is any integer. Okay, k can be any integer. You can also write like this. K is an integer, no problem. As long as you mention about the k, because the k is there, you need to define it. Okay, so k can be any integer. Okay, you also can check. Okay, you can substitute k with any integer. So you can take k equal to 3. So the outcome equal to 11 and -14. We replace into the equations. Yes, the equations remain true. Okay, now we have another example. 40x plus 16y equal to 88. Okay, because the GCD equal to 8. Okay. Okay, so 88 can divide by 8 because the outcome equal to 11. 11 is an integer, so it has infinitely many solutions. So we can find all the solutions just like in the previous example. Okay, so we divide the equations by 8, we obtain this equation, and then we solve this equation. 5s plus 2t, again because the value is small, so we can guess the value for the s and t. So because we have s and t, we can compute the particular solutions. Okay, because the particular solutions require these two values. Okay, without s and t, you cannot come out with your particular solutions. Okay, after we obtain the particular solutions, then we can come up with the general solutions. Don't forget this one is plus and this one is minus. And also don't forget to mention about the k can be any integer. Okay, this is the verification. Okay, now is the final topic, I think, in this lecture, which is about linear congruence. Okay, so the key point here is congruence. So that means we are dealing with the congruent relation, which is the triple horizontal line, and it is linear. Okay, so it also can be quadratic, cubic, and so on, but our interest is more on the linear congruence. So sometimes we need to solve a congruence or a set of congruence. So when it is a congruence, so that means it is single. Okay, so when it is a set of, that means there are more than one congruence relation. Okay, we start from with the single one, a congruence. Okay, so we need to solve a congruence or a set of congruence of one or more variables with coefficients in Zn. Okay, so for single variable linear congruence, the congruence is in the following form. Okay, we are given A, we are given B, and also we are given N, and your task is to find the unknown X, which satisfies the following congruent relation. Okay, we are given A, B, and N. Your task is to find unknown X. So a congruence of this type might have no solution or limited number of solutions. So it differs from the LDE. In the LDE, whether it has infinitely many solutions or there is no solution. But for the linear congruence, okay, it might have limited number of solutions, or there is no solutions. Okay, there is only two possibilities: no solution or limited number of solution. Okay, again we need to check the GCD of what? GCD of A and N. Okay, of A and N. So to find the GCD, that means we need to use the Euclidean algorithm. So the GCD, let's say the GCD equal to D, so we check if D doesn't divide B, this B. Okay, if we divide B by D, it is non-integer value, so that means D doesn't divide B. So the conclusion is there is no solution for the given linear congruence. Okay, but if the integer D divides B, okay, there are limited number of solutions. Okay, when limited, that means there are few solutions. So how many solutions? There are D solutions, where D is the GCD of A and N. If D divides B, that means there are limited number of solutions, means we can proceed with the steps to find the solutions. So we use the following steps to find the solutions. The first step is to reduce the congruence by dividing both sides of the congruence, okay, including the modulus N by D. Okay, just like the LDE, we divide all the values from left to right by the GCD value D. Okay, the second step is to find the multiplicative inverse of A modulo N. Okay, to find the multiplicative inverse, if you can guess. Otherwise, you have to do the extended Euclidean algorithm. Multiplicative inverse of A modulo N. Compute the particular solution x0 as follows. So once we obtain the multiplicative inverse of A modulo N, that means it is A to the power of -1. So we can find the particular solution. So the particular solution can be simply computed like this: x0 equal to B over D multiplied with the multiplicative inverse of A mod N. And then this product, we need to reduce mod N over D. Okay, so you need to do the modulo reduction. Okay, to make sure the outcome belongs to the Z N over D. Okay, that one is for the particular solution. And for the general solution, we have xk. Okay, we need to write k here, subscript k. Xk equal to x0, which is the particular solution, plus k times N over D. This time, the value for the k can be, it is not an arbitrary integer. Okay, because the value for the k this time is restricted only between 0 up to D minus 1. Okay, if D, for example, 5, so we have 0, 1, 2, 3, and 4. Okay, so the value for the k now is restricted between 0 up to D minus 1. Okay, example, solve the congruence 10x congruent to mod 15. So our aim is to find x. First of all, we need to check the GCD of A and N. Okay, so the GCD equal to 5. This is our D, but then B doesn't divides D doesn't divide the B, because 2 divides by 5. Okay, the outcome is a non-integer value. Okay, non-integer value. So that is why we need to use this notation and to conclude that there is no solution. The next one is 14x congruent 12 mod 18. Okay, we find the GCD by using the Euclidean algorithm. We obtain the GCD equal to 2, and 2 divides B. Our B equal to 12. Okay, so that means there are D solution. Because our D equal to 2, so there are 2 solutions. So first, because there are 2 solutions, we can find those solutions by using the following steps. The first step is to divide the congruence both sides left and right by D. Our D equal to 2, so we obtain this smaller congruent relation. The next step is to compute the multiplicative inverse of 7 modulo 9. Okay, and this task can be done by the extended Euclidean algorithm. Okay, we omit that step. We found that the multiplicative inverse of 7 mod 9 equal to 4, because 7 times 4 equal to 28, and 28 congruent 1 mod 9. So the multiplicative inverse of 7 equal to 4. The next step is to compute the particular solution. It can be computed by using the following equation. B over D times A inverse mod N over D. So we have 6 times 4 mod 9. The answer equal to 24, because 24 greater than 9. We need to reduce mod 9. It is equal to 6. So this is the first solution. So we remember we have D solution. Our D equal to 2. So we have 2 solutions. So the solutions are x0 and x1. So the x1 is computed like this. It is equal to x0 plus 1. Okay, N over D. So the outcome equal to 15. So there are 2 solutions, x0 and x1. Okay, why this one is 1? Back to the formula. The formula is this one, the value for the particular solution. Sorry, the value for the k, because k now equal to, okay, the value for the k is equal to 1. Okay, this one, k equal to 1. Okay. Now we can check, okay, if the question asks you to verify, yes, you can verify. So you can check, just substitute the value for the x equal to 6 and 15 and see whether the following 2 congruences are whole or not. So they are whole, so that means our answers are verified. Okay, wow, we have another topic. I think this one, yes, I think this one is the last one, Chinese remainder theorem, because it is related with the previous problem. Actually, it is related with the linear congruence. Previously we deal with a single congruence, but the Chinese remainder theorem is used when we need to deal with more than one congruences. Okay, describe the solutions to a system of simultaneous linear congruences. Okay, I know all of you know about simultaneous equations, right? So we have 2 or 3 equations, and your task is to need to find the solutions for those equations. So for congruence also relation also just the same case. We are given more than one congruence relations. So our task is to solve that system. Okay, when system means there are more than one congruence relation. So describes the solution to the Chinese remainder theorem can be used to describe the solution to a system of simultaneous linear congruences. That means we can find the solution for the simultaneous linear congruences by using the Chinese remainder theorem. So what is the theorem? So this is the theorem. Okay, suppose we have M1 up to M3 up to Mk. Okay, M1 up to Mk be pairwise relatively prime integers. So what does it mean? That means if we pair Mi and Mj where I and j are not equal, so all the GCD always equal to 1. Co-prime relatively prime means the GCD equal to 1. Okay, so if we pair M1 M2 GCD equal to 1. M1, M3 GCD also equal to 1. M2, M3 also GCD equal to 1. So all pairwise, you can substitute I and J with two different values. So all these M are relatively prime. Okay, so if all these numbers are pairwise relatively prime, we have another numbers denoted by A1 up to AK, can be any integer. There is no condition for this number, for these integers. Okay, for the M, the conditions, they must be pairwise relatively prime. Then the system of simultaneous congruences. Okay, this is the system. Okay, we have X congruent A1 mod M1, X congruent A2 mod M2 up to X congruent AK mod MK has a solution X. So now we are given all these values A1 up to MK, we are given values M1 up to MK. Our task is to find the unknown X which can simultaneously solve all these congruences relations simultaneously. Okay, so we are looking for the value of X because X is the solution. Okay, so the solution is an integer. So let's say we denote the solution as C. Okay, the first solution is C, the second solution is C prime. That means we have more than one solutions. So these two solutions actually are congruent to each other modulo the product of all M. Okay, both solutions, solution number 1 is C, solution number 2 is C prime. So these two numbers are congruent modulo the product of all the modulus. Okay, this is the example. Okay, you are given two congruence relations. X1 congruent 1 mod 5. Sorry, X congruent 1 mod 5. X congruent 9 mod 11. Your task is to find X which can make these two congruences true. Okay, these two congruences simultaneously true. So note that the GCD of 5 and 11, M1 and M2 equal to 1. Okay, the GCD equal to 1. So that means the congruence relations 1 and 2, the system has a solution. Okay, has a solution. So what does it mean? That means before you compute the solutions, the first step is to check the GCD of the modulus. Okay, if the GCD of the modulus equal to 1 for all pairwise modulus, this time we only have 2, right? Okay, so if the GCD equal to 1, then that means the solutions exist. When the solution exists, then we can proceed with the calculation. So this implies that because the GCD of the modulus equal to 1, there is a solution for the simultaneous congruences 1 and 2. Okay, so how to find the solution? First of all, you need to know how to convert from congruence becomes equation. Alright, okay, convert from congruence becomes equation. So how to do it? How to convert from congruence becomes equation? So we back to the definition of congruent relation. So X congruent 1 mod 5 based on the definition means that X minus 1 divided by 5, it is equal to Q. Okay, if you can see here, from congruence now it becomes equation. So we rearrange this equation. So for X, so we have X equal to 5Q plus 1. Okay, just exactly the equation number 3. So that's the way how we convert from congruence becomes equation. We're back to the definition of congruence relation. Okay, so we convert the equation 1 to equation, so we obtain equation number 3, where Q, don't forget to mention about Q, because Q is suddenly appear, we need to define it. So Q is an integer. Next is just to substitute the equation number 3 into equation number 2. In the equation number 2, we have X congruent 9 mod 11. In equation number 3, we have X equal to 5q plus 1. So we just simply substitute x to this side. So we have 1 plus 5q. Next, we want to eliminate 1. How? By minus 1 to both sides. So minus 1 here, so the remaining is 5q. Minus 1 here, the remaining is 8. Okay, so we minus 1 at both congruent sides. So the remaining congruence relation is 5q equal to 8 mod 11. So in this case, we have a linear congruence. Okay, a linear congruence. So we need to solve this linear congruence for the integer q by using the steps that we learned in the previous topic about the linear congruence. Okay, first of all, to find the value for the q, we consider the GCD of 5 and 11. So the GCD equal to 1, that means there exists the multiplicative inverse of 5 modulo 11. Okay, so the multiplicative inverse, we can either we guess or we do the extended Euclidean algorithm, so we can omit that step. So the multiplicative inverse is equal to 9. Okay, so using this value, we can find, okay, the multiplicative inverse of 5 modulo 11 equal to 9. The next step is to multiply this congruence both sides by 9. So we have this one and this one. Okay, so 5, 9, q congruent 8, 9 mod 11. So because 5 times 9 equal to 45 and 45 congruent 1 mod 11, so we can substitute 45 with 1. Okay, we can substitute because 45 we do the modulo reduction also, you obtain the value equal to 1. Okay, so we can substitute 72 mod 11 equal to 6, we can substitute. Okay, this one both similar lah maksudnya. Okay, 45 congruent 1 mod 11 because 9 is the multiplicative inverse of 5. Okay, so also you can do the modulo reduction. 45 mod 11 equal to 1, so you can replace this one is 1. 72 mod 11, we do the modulo reduction, it is 6, so we replace by 6. So next, so we have q congruent 6 mod 11. So back from congruence, we need to convert it to equation form. So we have equation, this equation, q equal to 6 plus 11 k, where k is an integer. Okay, k is suddenly appear, so don't forget to define what is k. So k can be an integer, so that means we can replace k with any integer. It is the value for the q. So for simplicity, we can take the simplest value for the k equal to 0. So when k equal to 0, so means our q equal to 6. Our q equal to 6. But remember, our aim is not to find q, but our aim is to find x. So we back to the equation of x. Our equation of x is equation number 3. X equal to 1 5 plus 5q. Previously, q is unknown. So once we have the value for the q, we can substitute the value for the q. Then we obtain the value for the x. Okay, so this is the equation. X equal to 1 plus 5q. Substitute q equal to 6. So we obtain our x equal to 31. So if we verify, we substitute x into both congruences. Our x is 31. These two congruences are true. That means our value x, the outcome x is verified. So if we take different value for the k, we obtain different value of q. Because in the equation of q, the k can be any integer. This one, q can be any integer. Okay, so you can replace k with any integer. So we take k equal to 0, we obtain q equal to 6. We substitute k with 1, so we obtain another q, which is 17. So we substitute 17 into the equation number 3. So we obtain different value of x. This time we obtain 86. If we verify, we substitute 86 to both congruences. Again, both congruences also true. Okay, or hold. So that means, okay, 86 also solutions for the given congruence relation. So we have two solutions now. If we substitute k with different integer, for example 2, 3, 4, 5, and so on. So all these values will give you different q, and different q will give you different x. Okay, so all these solutions are congruent to each other. For example, 86 congruent to 31 mod, we multiply the modulus value. 5 times 11 equal to 55. Okay, so this congruence is true. Okay, so in the previous example, you only deal with two congruence relations, and you need to solve it simultaneously to find x, which can solve the two congruence relation. So what happens if I give you more than 2? Okay, for example 3. Okay, so in this problem, just like the previous problem, we need to find the x which can simultaneously satisfy these three congruences. Okay, because the question asks you to solve the following system. Okay, instead of using the previous steps, we can do simpler steps actually for when we are given three congruences. Okay, how to do it? First of all, we compute the capital M. The capital M is we multiply all the modulus values. Okay, but remember, first of all, we need to make sure that all these congruences are pairwise, relatively prime before we proceed. So we need to check first. Okay, we need to check GCD of 3 and 5. Yes, it is equal to 1. GCD of 3 and 7 also equal to 1. And the last pairwise pair is 5 and 7. Okay, 5 and 7 also equal to 1. So yes, this system has a solution. Then you can proceed. Okay, the first step is to compute the capital M. The capital M is obtained by multiplying all the modulus value. So we obtain M equal to 105. Next is to compute M, capital M1, capital M2 up to capital MK. So how to obtain capital M1? Capital M1 equal to 105, which is the value for the M. We divide by M1. M1 equal to 3. Okay, next is capital M2. Capital M2 equal to M divided by M2. M2 equal to 5. And the final M is M3 because we only have M3, right? Small M3. So we find until the capital M3. So the value is capital M. We divide by M3. M3 is equal to 7. So the outcome is 15. So now we have capital M, capital M1, capital M2, and capital M3. We can proceed to the third step. In the third step, we need to find the multiplicative inverse of each capital M1, M2, and M3. Okay, capital M1 inverse, capital M2 inverse, and capital M3 inverse. Modulo M1, M2, and M3. Okay, so if you can guess. Otherwise, we need to do the extended Euclidean algorithm. So we obtain the multiplicative inverse. The first multiplicative inverse is 2, the second one is 1, and the third one is 1. Okay, once we obtain all these values, now we are ready to compute the solution, because the solution can be simply computed by using the following equation. Okay, so we just simply insert the value for the A1, multiply with capital M1, multiply with the capital M1 inverse. Then we add with A2 times capital M2 times capital M2 inverse. We add up to K. So because we only have until capital M3, so we have the following equations. After we compute all these values, then we obtain the value equal to 233, because 233 is larger than 105, which is the capital M. So we need to reduce it modulo 105 modulo M. So the value is 23. So 23 is the solution for the given system. So 23 can solve all these three congruences simultaneously. Okay, 23 can make all these three congruences true. Alright, so that's the end of this lecture. Thank you, class.